What specific problem does the PRADA framework aim to solve in the context of chain of thought reasoning and knowledge distillation?
The PRADA framework aims to address the generalization degradation observed in knowledge distillation processes for chain of thought, COT reasoning, particularly when transferring knowledge from a large teacher model to a smaller student model. A significant issue is that the smaller student model tends to memorize the pre-trained COT paths instead of maintaining the generalization ability of the larger teacher model, leading to poor performance on unseen domains. PRADA tackles this by incorporating prompt learning layers to facilitate the acquisition of domain-agnostic knowledge and applying domain adversarial fine-tuning to enable the model to learn invariant domain features. This approach enhances the cross-domain generalization versatility of smaller models while retaining the COT reasoning capabilities of the teacher model, effectively mitigating the shift from generalization to memorization. Through extensive empirical evaluations, PRADA demonstrates substantial improvements over previous COT knowledge distillation methods in cross-domain scenarios.
How does the proposed PRADA method work? Please illustrate step-by-step the processing between the teacher model and the student model, including the role of p-tuning and domain adversarial fine-tuning.
The proposed PRADA method operates in a structured manner involving both a teacher model and a student model. First, the teacher model, specifically a large LLM like GPT-3, generates diverse chain of thought, COT reasoning responses for a given task using a zero-shot COT prompting method, which allows for the creation of multiple reasoning outputs through stochastic sampling. These outputs are then filtered and formatted into question completion pairs, which serve as the training data for the student model. Next, the student model employs p-tuning, where continuous prompt embeddings are integrated to enhance its reasoning capabilities and stability. This involves updating the prompt embeddings during training to optimize performance on the source domain data. Finally, domain adversarial fine-tuning is applied, where the student model is trained on both source and target domain data, utilizing a domain classifier to learn invariant features across domains. This dual approach of p-tuning and domain adversarial fine-tuning enables the student model to generalize better to unseen domains while retaining the reasoning capabilities learned from the teacher model.
Can you provide a simple yet illustrative example demonstrating the inner workings of PRADA using a specific dataset or question? Walk through the main algorithm steps with this example.
To illustrate the inner workings of PRADA, let's consider a specific example using the GSM-8K dataset, which involves arithmetic reasoning. First, the large teacher model, such as GPT-3, is prompted using the zero-shot COT method to generate diverse reasoning responses for a question. Say, what is 15 plus 27? This generates multiple reasoning paths, such as, let's think step by step, 15 plus 20 equals 35, then 35 to 3 equals 32, so the answer is 42. These outputs are filtered to retain only those that match the correct answer, forming question completion pairs. Next, the student model employs p-tuning layers to learn from these pairs, enhancing its ability to generate coherent responses. During training, domain adversarial fine-tuning is applied, where the model learns to distinguish between source domain, GSM-8K, and target domain data, ensuring it captures domain-agnostic features. This process allows the student model to generalize better to unseen arithmetic questions, ultimately improving its performance on tasks requiring complex reasoning, as evidenced by the accuracy improvements shown in the results.
What are the theoretical or practical benefits of using the PRADA method over existing COT knowledge distillation methods? How does it improve generalization across domains?
The PRADA method offers significant theoretical and practical benefits over existing COT knowledge distillation methods by enhancing the cross-domain generalization capabilities of smaller models while retaining the reasoning abilities of larger teacher models. Specifically, PRADA incorporates prompt learning layers that facilitate the acquisition of domain-agnostic knowledge, allowing the student model to learn invariant features across different domains. Additionally, the domain adversarial fine-tuning applied in PRADA mitigates the effects of domain shifts, which is a common limitation in traditional knowledge distillation approaches that often lead to memorization rather than generalization. Empirical evaluations demonstrate that PRADA substantially outperforms previous methods, as evidenced by improved accuracy across various datasets, indicating its effectiveness in adapting to unseen domains. Overall, PRADA's innovative framework addresses the generalization degradation typically observed in knowledge distillation processes, making it a robust solution for enhancing model performance in diverse scenarios.
How was the PRADA method validated? What experimental design, datasets, and metrics were used to demonstrate its effectiveness?
The PRADA method was validated through extensive empirical evaluations using 12 datasets spanning 4 categories of complex reasoning: arithmetic reasoning, symbolic reasoning, common sense reasoning, and other reasoning. The experimental design involved comparing PRADA-enhanced models against several baseline methods, including pre-trained models like DaVinci 002 and FLANT 5 Large, as well as fine-tuned models such as fine-tuned COT and specialized. The effectiveness of PRADA was measured using accuracy, ACC, and the improvement in accuracy, delta, across these datasets, ensuring that all methods followed the same experimental settings for a fair comparison. Results indicated that PRADA consistently achieved the highest accuracy, with notable improvements, such as over 10% in accuracy for Llama 3-8B plus PRADA on the SVAMP dataset compared to its pre-trained counterpart. Additionally, the analysis included experiments to assess the impact of removing the domain classifier and p-tuning layers, further demonstrating the importance of these components in enhancing model generalization ability.
What specific results were achieved with PRADA, and how do they compare with the baseline models on the 12 datasets mentioned in the paper?
The PRADA framework demonstrated significant improvements in accuracy across all 12 datasets compared to baseline models. For instance, the Llama 3-8B model enhanced with PRADA outperformed its pre-trained counterpart by over 10% in accuracy on the SVAMP dataset. The empirical evaluations indicated that PRADA consistently achieved the highest accuracy across various arithmetic reasoning tasks, showcasing its effectiveness in enhancing cross-domain generalization. In contrast, baseline models such as specialized LLM, fine-tuned COT, and MT-COT did not match the performance levels attained by PRADA, highlighting its superiority in maintaining reasoning capabilities while adapting to new domains. Overall, the results underscore PRADA's ability to significantly enhance the reasoning performance of smaller models in complex reasoning tasks.